we supposedly moved a month ago, but we haven't. So for a little time yet, I'm in 5147 in the Dentistry Pharmacy Center because I'm also part of the faculty. Well, dentistry is not part of the faculty of dentistry. I'm also in the dental school. The point of this is I'm quite happy to answer questions when you ask them during class. However, I have noted over the years that sometimes people are shy and don't like to ask questions in class. And I'm always willing to, unless I have an 11 o'clock class, which I hope you can understand, might mean I want to beat a hasty retreat from here, but normally I don't, and I'm quite happy to answer questions after class. The point of telling me I have 2 offices isn't bragging, is that if you just decide to spontaneously show up, you have a 50-50 chance of picking the wrong office. So if you do have a question that is more than something you can ask either during class or after class or even before class, make an appointment, and then you can even pick which office you want. And I will be glad to answer your questions there. So again, it's just, if you're in a hurry and you decide you're going to zip by and answer the quick question, and the prof isn't there, it can be a little bit of a hassle. So I'm just telling you, I'm in 749 up here, or 5147 over there, just so that you don't get yourself where you're running between places and trying to find them. The other thing is, yesterday I received an email about recording the lectures. I don't mind. I forget the person's name who sent me the email, but I don't mind. So you know who you are, and please go right ahead. And if anybody else wants to talk. Okay, topic is, it says vision in your course syllabus. It says special senses, and what we do is humans have lots of senses, more than the traditional 5. But because of time constraints, we'll talk about 2. One is vision, because we are primarily visual animals, and the second one will be hearing. However, if you hang around and do a degree in honors physiology, we do have a course at the 400 level where we talk a bit more about vision and hearing and vestibular and pain and all the other senses that we have. We're going to use those 2 as a model, because if you understand roughly how those work, you can figure out pretty easily how all the others work. But I do have a few introductory sort of remarks. And so, since we're really looking at using vision and hearing as models for sensory perception, I guess it behooves us to define it. And sensory perception basically amounts to the deconstruction of the external world and subsequent reconstruction of the internal representation. In other words, you have to convert let's use vision, you have to convert a chair into some kind of electrochemical event, because you can't internalize the chair itself. You have to internalize how your central nervous system converts in the case of vision, the light energy reflected off the chair into a series of action potentials that the brain reconstructs and gives you the feeling of what you see, feel, touch, and hear. Okay, sensory endings, whatever kind they may be, respond to a particular type of energy applied to them or near them. And this particular stimulus is called the adequate stimulus. This is very simple. The old joke about shining light in your ear, you don't see it. Well, yes, that's right, because photons are not the adequate stimulus. Why did you use a guide on me? Anyway, photons are not the adequate stimulus for the visual, for the auditory system. Vibrations in air are, so we just have to have that's not the word. So, you know, in the case of vision, it's photons of light energy. Okay, that's right. And case of hearing, it is pressure waves in air. In the case of the pain system, it would be stimulation of particular nerve endings, and each of those would be the adequate stimulus for that particular sensory system. Okay, so a few more words and definitions, and that is that sensory endings that respond to a particular type, whoops, might help if I was on the same page as you. The energy has to be that adequate stimulus. In the case of vision, photon energy must be converted to electrochemical energy, i.e. either excitatory or inhibitory post-adaptive potential, and then if it's excitatory, hence into an action potential. Look, it does say up there action potential or change in membrane potential, and that's because most of the retina does not use action potentials, but changes in membrane potential, like an EPSP or an IPSP that doesn't summate. So whatever that adequate stimulus is, that form of energy, be it photons or pressure waves in air, must be converted to action potentials or a change in membrane potential. And this conversion of one form of energy into another is called the primary transduction process. So when you convert some photons of light into a change in membrane potential, that's the primary transduction process. Now, all sensory systems tend to work somewhat along the lines of these four statements. Preservation of nearest neighbor relationships and organizing of the sensory nervous system from the receptive surface to the cortex. What that means is that when you look at, say, these bars or whatever, 1970 form of design was, but that's when they built it. You know, if you were to stare at these bars and the cells that are responding to this point on this edge and the cells responding to this point on this edge are actually sorted out and are side by side, and if you trace the output of the cells from the retina back all the way through to the first relay station, the lateral geniculate body, and ultimately the occipital cortex, you find that the cells that see things that are adjacent in visual space stay together. You don't have a cell that's looking at one spot and a cell, so you've got a cell that's looking, say, at this spot, this corner, and the cell that's looking at this corner here. You don't have them side by side. They're here. The cells, you don't have this one and this one side by side, and the one in the middle here, it would be this one, and the cells would go point by point right down. They would be in a nice, organized fashion. It doesn't necessarily mean they're in a straight row, but they're side by side. Okay, so you tend to preserve the cells that are processing things that are adjacent in visual space stay together. Interestingly enough, the cells that hear frequencies in your ear that are very closely related, they're side by side, and they tend to stay side by side or be in very close proximity all the way back to the auditory cortex. Okay, the temporal or frequency tuning is fundamental to sensory analysis. The CNS pays particular attention to signals at varying time. All that means is that you tend to have frequency, the intensity, and loudness, if you like, tend to be signaled by changes in the frequency of the action potentials. Also, it tends to say that if you have something going on for absolutely the same for long periods of time, the brain starts ignoring it and not paying attention. A simple one like that is until I mention it to you, and instantly you will then, as soon as I mention the example, you will suddenly all become consciously aware of it because you shift your attention. But you probably don't pay too much attention to either the pressure on the gluteus medius and the chair, now you do, nor are you probably consciously thinking about whether the room is hot or cold right at this instant in time until I just mentioned it, because it isn't changing. And so the CNS says, well, if it's not changing, it probably isn't important. We're not going to worry about it. Okay, parallel processing of different functional aspects of the stimulus. Okay, all that means is all these guys that talk about parallel processing in computers are just replicating what your brain's been doing for a long time. And that is, when it comes to vision, you're analyzing shape, color, form, movement, all at the same time. But not necessarily by the same cells, but it's all happening at the same time. So that's a form of parallel processing. Same thing in hearing. You're interested in how loud it is, what frequency it is. That's not it for hearing. You either know the pitch, high or low, and if it's varying in time. Anyway, so that's okay. Hierarchical or serial processing, whereby higher levels of the sensory pathway combine inputs from lower levels to drive new, more complex sensory constructs. All that basically means is, if you got parallel processing going on, color, shape, movement, they just take those three. You can do binocular or depth perception, anything like that if you want to. Those are all being done separately, but someplace in the central nervous system, you don't see, something in color, then you see it move, and then you notice how deep, or the depth perception. You see it all at once. So all it's saying is it takes it apart into its component parts, and someplace in the central nervous system puts it all back together to give you one combined sensory experience. So you see the shape, the color, and any movement, and how any three-dimensional aspects all at the same time. Oh. Because we're going with definitions, we might as well add a few more. This one's kind of simple because you've seen this before, and I've used the terms before. But if somebody starts talking about generator potential, it should be a signal to you they're talking about a sensory system, because if you look at the definition of the generator potential, it's a non-propagated gradient potential, usually polarizing. Okay. Thus, it resembles an EPSP recorded from a sensory nerve or specialized sensory engine. Okay. So generator potential just is could be an EPSP. It could also be an IPSP. But because you call it a generator potential, it signals to the listener that you're talking not about some peripheral nerve, peripheral motor nerve. You're talking about something to do with the sensory system. Okay? The generator potential may also be hyperpolarizing if potassium leaves the cell, and the magnitude of the generator potential is usually proportional to the strength of the stimulus. Well, that's the definition pretty much of an EPSP or an IPSP. So, okay. Where are we next? Oh, we're on the island. Now, this is a bit of a bummer because I didn't bring the one. I'll get some free batteries from the university days alongside. Anyway, okay, we're going to go through the anatomy of the eye. Unfortunately, I feel somewhat incapacitated since I don't have a functioning. I always live in hope that it might rectify itself. Amazing. Okay, so we're going to start. We're going to start here and work our way through the layers as the light passes through it. All right, so the first, excuse me, the first thing you note about an eye when you look? No. Let's not be temperamental. Okay, the first layer that the light will pass through is a thin membrane here called the conjunctiva. It is just a thin membrane that covers the cornea. And you sometimes see it referred to when people talk about whether or not you have conjunctivitis. So that Visine and stuff that says it's going to take the red out is usually talking about some kind of an inflammation that's taking place over this conjunctiva. Oh, just to keep me on track, because I can wander off and talk for hours on this. They only give me 3, so I have to be careful. Okay, the next part that the light passes through is a little dome-shaped structure called the cornea. And the cornea is hopefully a nice, smooth curve. Sometimes it's considered to be like a slice off of a nice, take a spear, you cut a nice little slice through it, nice, even curve on it. And it is the primary, contrary to what people may have told you before, for my purposes, remember what I tell you, not that I'm necessarily always right, but since I wrote the exam questions, I don't admit to be infallible, but I think you'll find that if you read most textbooks, you'll find that the cornea is the strongest component of the light focusing system of the eye, not the lens. The cornea is much like the coarse focus on your microscope, and the lens is kind of like your fine focus. Okay? The cornea, now you want to dive. The cornea is a specialized portion of the eyeball called the sclera. And the sclera is the white of the eye. It is a tough, fibrous connective tissue that makes up the main portion of the eye. So the cornea is really a modified or specialized portion of sclera. Okay. So the white of the eye is the sclera, the cornea is the transparent portion through which the light passes. Now, right behind that cornea is something called the anterior chamber. Well, that name is fairly obvious. It's a small chamber and it's up front, so there's the name. And it is filled with a fluid called aqueous humor. Aqueous humor. Aqueous from the Latin for water, and humor, H-U-M-O-R. Some people like to spell it H-U-M-O-U-R, whatever. Gets its name from the fact that when the early anatomists were going in and chopping things up, and they cut into behind the cornea there, and opened up the anterior chamber to the outside, it was a thin, watery fluid that ran out. And since they said, well, it looks like water, it runs like water, we'll call it aqueous, but they didn't know what else it might be. And so this is in the day when if you didn't know what it was either a humor or a spirit or something like that. And so aqueous humor just got that name because it was water looked like, and they didn't know what it was. Now, of course, we know what it is nowadays. It's just like tissue fluid. But you'll find that in science and medicine, old names die very, very hard. Okay, we can't really see it on that one, so that must be time to change it. Okay? Okay, so, going on me now here. Okay, so here we have the cornea, And here we have the anterior chamber. Here, and the aqueous humor is secreted by the ciliary body, which is this little dude down here, kind of, okay? This is the iris, okay? We haven't got there yet. Here's the cornea, the anterior chamber. Here's the iris. That's the colored portion of the eye. It's either blue or brown or some combination thereof, depending on what kind of pigments and how much you have. And you will of each one. And the anterior chamber is continuous here. And so the ciliary body here secretes the aqueous humor, and it comes up and circulates through here. And the aqueous humor is drained by the canal of Schlemm, after the guy who described it, which is the old tradition. Okay, so if you like, the ciliary body secretes it, and the canal of Schlemm, which is, if you wanted to have to define it, it's kind of where the sclera and the cornea have their junction on the inside. So you have the circulation of aqueous humor that from the ciliary body out into the anterior chamber, and kind of at the corner of the eye, down here, this part here is the posterior chamber. So here's the anterior chamber, comes back here, this is the posterior chamber. So if you like, the ciliary body squirts the stuff out, runs it up, and it comes up and is drained up there. So the anterior and really the posterior chamber are both filled with aqueous humor, since it's all kind of one continuous chamber anyway. Okay. Now, let me tell you, let's go back to the, because I don't think that had. Okay. So what we've been looking at is this little bit down in here, and correspondingly will be up here. So if we go back, the light passes through the conjunctiva, gets its initial focus by the cornea. The light then passes through the anterior chamber, through the pupil, which is just the space in between the two leads of your iris, and get the crystalline lens, as it is sometimes called. Okay? And the lens, as I say, is that portion of the eye that helps do the final focusing. And it, when you are young and your age, is relatively flexible. We won't get into, well, yes, we will. So this is a good place to get away from anatomy and go into some physiology. Okay, so cornea does most of the focusing, much more powerful than the lens, and the lens is a flexible lens there that is suspended in position by some zonal fibers we'll talk about in a second. But what the lens does is allow the eye to accommodate. And so accommodation is a process by which the curvature of the lens is increased. Occurs during near vision, and the anterior curvature of the lens is the most effective. So it's the front part that is the most effective. So if we go back. So what we're saying is that the lens, the curvature here of the lens is can be changed. It changes especially during near vision. Of course, the posterior curvature also is affected some, but the anterior is the most. Okay. Okay. So we have the process that we can do this focusing bit, our accommodation. But just for a very brief little dip into, to remind you a little bit about something you may not wish to remember from your days when you were taking physics, if you took physics. And that is that what is happening with the cornea and the lens is called refraction. And refraction is simply the deviation of light from a straight path as it passes through one medium to another. And this can affect its velocity. But anyway, okay, so what we're saying is the light's passing straight through, and because of the cornea and the lens, you deflect it from a parallel path. The simplest example I can think of for those who may or may not like physics or took it, who would like to forget it, is you all played with magnifying glasses as kids, I'm sure. And you may have noted that if you move the magnifying glass back and forth from a surface on which the light is falling, it can go from a circle to a very fine point, and that if that surface that you're playing with the magnifying glass happens to be one of your siblings, then when you get it to a really fine point, you can have fun watching them scream in pain as you burn them. Okay, I see a few people smiling. That's good. Shows we have a few people out there that have an inquisitive mind. Okay, so what you've done is you've deflected those rays of the sun from a straight path to a curved path. And as you bring the magnifying glass back and forth from the surface on which you're shining it, when you bring it into sharp focus, you've deflected the most, done the most refraction. Okay. Okay, so the distance from the refractive surface, the cornea, to the point where parallel light rays converge is the focal distance. Well, that's the same thing as moving the magnifying glass back and forth. So the reciprocal, that's 1 over the focal distance in meters, is a measurement called the diopter. And this is what unit your eye doctor uses, be an ophthalmologist or optician, uses to set the strength of your corrective lenses. So the cornea has a refractive power of about 42 to 43 diopters, which means that parallel light rays striking the corneal surface will be focused about 2.4 centimeters behind it, which should be the distance between the cornea and the retina. And while we haven't talked about the retina, I would be surprised if you hadn't heard that that's where all reaction and vision takes place. So there you have some like words, some like pictures, same sort of thing. All we're saying is, here's, will it work? Here's the surface of the cornea, here's the surface of the retina back here. So from here to right there is the focal distance. So the refractive power of the unit here is 1 over the focal distance in meters. Okay? Okay. So there's so much for our dip into physics. And we will now look at how we put this into practical use. The lens is held in position by behind the iris by suspensory ligaments, and those suspensory ligaments may also be called zonual fibers. You can use, well, I typed it right, it might have been better. Suspensory ligaments are called zonual fibers. That's a bad deal. Okay. That's not important except for the fact that both names, either name is quite happy, and whichever one you choose to use, I'm reasonable, bilingual, and we'll call either one. Okay. Now, these zonual fibers, or suspensory ligament, whichever way you like, are embedded in a donut-shaped bit of smooth muscle, very much like a sphincter. This donut-shaped bit of smooth muscle. Okay? So So as the picture shows, when the ciliary muscle is relaxed, okay? So the muscle's not contracted, so it's relaxed. There is, as it relaxes, it pulls on those suspensory ligaments. And this tends to thin out the lens a bit, reduce the curvature, and set, your eye is then set for distance vision. So at rest, your eye is set for distance vision. Okay? So now you want to do some accommodation. You want to refract that light a bit more so you can bring it into something near the focus. So what happens? Well, now the muscle, the ciliary muscles are contracted. Well, that means the muscle shortens. That means the circle is going to get smaller. So that means that there's going to be less tension on the suspensory ligaments. And that means that the lens, so then the lens gets thicker and is focused for close vision. Okay? So you figure what you're doing is you got a circle this big when you're at rest, you got a circle this big when you're looking up close, and that changes how much tension is on those suspensory ligaments, which changes how much pull there's going to be on the, especially the anterior portion of the lens. Okay? That's why reading too much, you can get tired eyes because you're forcing that ciliary muscle to stay contracted for long periods of time as you're accommodating for up close. Okay, well, being biological systems, not everything works the way it should. Now, if you have, and unfortunately, because I got 3 different classes today, I've got my stuff spread around to death. I don't have something to write on the board there. But if you have perfect vision, want to do old 20/20 vision, you have what is called emetropia. I will spell it slowly since it seems that if you don't have it on a memory stick, you don't have it anywhere. I guess they don't believe writing anymore. Okay, emetropia. Perfect vision. E, M, M, E, T. So emet. E, M, M, E, T. R, O, E, I, A. Okay? So if you can sit there, smugly sitting there with no spectacles or contact lenses, and see everything at 20 feet that you should see at 20 feet, you have 20/20 vision, so you have emetropia. However, we will soon take some of the wind out of your sails and be sitting there feeling smug that your vision is perfect. We go down the list here. Okay, so the first thing we have is myopia. You probably think of it as nearsightedness, and its most common cause. Now, note the phraseology, please. The most common cause. This is not ophthalmology. You'll just have to wait till you get to medical school. For all the various and the sundry problems that can go wrong, because you haven't quite made it yet, I tend to stick to the most common cause if I bring up a problem or a disease or a defect. And I do not go into all of them. So if you know 5 or 6 other reasons why a person may have myopia, blessings on you. But for our purposes, I give you, and I say this not trying to be miserable, but I have had students come up and say, well, I know this, and this, and yes, that's very good. And you're, most of the time, the students that do this are absolutely right. But then there are other students that don't have that benefit, so I just stick with the most common. So bear with me if you happen to know more about some of these things, disease states and such. No, this isn't a disease. Okay, so we'll put up some pictures in a second. But generally the eyeball is a little too long. Instead of being kind of almost spherical, it tends to be a kind of a flattened oval. Okay, you may go the other way and have hyperopia, which is more commonly known as short-sightedness. And again, the most common cause is the eyeball's too short. It's not quite as spherical as it should be. It's kind of a flattened circle. Okay, now there is another one, and this is the one for those that are sitting there with emmetropia right now feeling very superior, is that if you live long enough, you might get presbyopia. And what happens is as you get older, the lens starts to stiffen, and it means that it's not as elastic as it was when you're your age now. And so the poor little fibers try to pull on the lens, and it just doesn't quite work as well as it used to. So if you like, these three here really involve the lens. But there's a fourth one you can have, and it's called astigmatism. And again, there are lots of causes of astigmatism, but one of them, the most common, is the fact that the curvature of the cornea is not uniform. In other words, it's not that perfect slice off of the sphere. It's got humps and bumps in it, and that distorts the passing of light through it. Okay, so here we have, there we are. You can check to make sure I spelled it right. Emmetropia up there. Okay? So what happens is, normally the light comes in, it gets refracted, and comes to the nice sharp focus back here on where the retina is, which we haven't quite got to yet. If your eyeball is too long, so it's got kind of that flattened oval shape, what happens is the focusing system here, because you're biologically programmed to have a certain diameter eyeball, the light comes into focus here, but the retina's back here, and so just like with that magnifying glass, the light comes into focus and then it starts to go out of focus, and so you get what's known as a blur circle. So if you put a concave set of lenses here, you can push the image back and bring it into focus on the retina. Now that concave lens is sometimes called a negative lens. And when you look at if you have your eyes checked regularly and you see positive or negative, the first thing you should see, assuming all the ophthalmologists use the same prescription forms that I've seen, the first thing you'll see is a positive or negative number. If it's a negative number, not that you wouldn't know already, it means you're nearsighted. And then the next number is the strength of the lens in diopters to push the image back onto the retina and into focus. If you're farsighted, the eyeball is too short. You can see the difference here. Here's your nice spherical emmetropic eye, and here's the other. And this one, the eyeball is too short, and so the system here is set up to focus, but unfortunately it's set to focus back here instead of up here where the retina is. So again, you're in a blurred circle. And so now you put a convex lens in front, sometimes called a positive lens, and it brings the focal point forward so that it's in focus on the retina. Okay? Now, if you have astigmatism, and if that astigmatism is due to the most common cause, which is a problem with the surface of the cornea, they will give you another set of numbers on your optical prescription. And what that is it's a series of numbers with some degrees on it, and then some positive and negative numbers. Now, if you picture a circle, and if Picture that clock was round like we use it, instead of rectangular. But if this, it shouldn't be too much of a stretch. At the top where the 12 is 0 degrees, where the 3 is 90 degrees, where the 6 is 180 degrees, and where the 9 is 270 degrees. Now picture that just right looking at your cornea. Same sort of thing. So that's what all this gas here is about. Okay? So they will go in and they will figure what plane across the cornea you got a problem with, a hump or a bump or a valley or a pit in it. And then what they will do, they will prescribe a cylindrical lens. Now I call it a cylindrical lens because, well, this is fairly close to the cylinder here. Close enough that you can use your imagination is you bring down, if you were to slice off various pieces of this, you would have a lens that looks like this one, and the thickness would depend on if you cut here or if you cut over here. Okay? And vice versa, you have the negative curvature. So this is much like a convex lens, is like a concave lens. And so what they will do is go in and you'll see, should see for each eye 2 sets of numbers, a positive and negative number of diopters. That's telling you it's negative number or you're nearsighted, positive number you're farsighted. Like I say, you already know that, but it's always nice, good to know that they know, the prescribing person knows it too. And then the other set of numbers is if you have an astigmatism, there'll be a set of degrees. Tell you what plane the pit or lump or hump in your cornea is. And then the other number will be the strength in diopters of the cylindrical lens that will compensate as best they can for the defect in the curvature of the cornea. The astigmatism is probably the hardest to overcome because usually it depends on if you've got some kind of major deformity, sometimes it's in several different planes and it's difficult to correct. Okay, now, let's we can go back here. Okay, now, so the light goes through the conjunctiva, through the cornea, through the aqueous humor, hits the lens, and the final focus takes place, and the light now passes through this great big space back in here. And I've seen several ways that they name it. This textbook happens to use the term vitreous humor here. I've seen it called vitreous humor, but in most cases I've seen it also is vitreous chambers, like you have anterior chamber, posterior chamber. More modern books, except that none of them have, those that have what we call a vitreous chamber tend to have a lousy diagram for the rest. That's why the old picture. So this is sometimes called the vitreous chamber and is filled with, as the sign says, vitreous humor. Vitreous humor, vitreous, again, goes back to the Latin, which was the language of science for a long, long time. Kept the masses from knowing what they were up to, means glass. Vitreous means glass. So if you've been in some zoology courses and other courses around and you hear them talk about studying something in vitro, well, that means it was in a glass chamber. Okay, so the vitreous chamber gets its name because when they opened it up, just as they were hacking away with eyeballs in the front and continued, what came out of the vitreous chamber was a very thick, viscous, gelatinous substance. And it reminded them of molten glass. Now, when it's really hot, glass kind of glows red, but as it's cooling, it loses the red. It's still quite hot and it flows. And so to them, it reminded them of glass. But again, they didn't know what it was. And so the good old catch-all term of humor was attached to it. So they called it vitreous humor. We now know it's a very clear, gelatinous material with protein and collagen in it. Now, it is under pressure to help keep the eyeball inflated. And the reason for that is, we think, try and attribute reasons to, how various parts of the body work when we don't really have the instruction manual from the manufacturer. But what we think is, if the eyeball was a rigid structure and you got a blow, it could crack or break much like a leg or an arm. Well, that's no good because you can't put vitreous humor back in and let it heal. So we figure a nice, tough, fibrous, connective tissue sphere, while it hurts if you push on it too hard, will give a bit. Like I say, it may hurt, but it'll bounce back and you still can see. Unfortunately, if you do puncture a vitreous chamber and the vitreous humor starts to ooze out, they can't do anything about it. But we think it's under a few millimeters of mercury pressure to keep it inflated like a balloon. You can deform it painfully, but a bit, without rupturing it or tearing it, which means you may go through a bit of pain, but you can still see. Whereas if it does get punctured, it oozes out and you lose the sight in the eye. Okay, we're getting rapidly close to the end. Okay, so then we'll get through the gross anatomy, which is almost done, and then we'll be done when we pick up. If you look back, through an ophthalmoscope, or if you haven't had the opportunity, this is what your eye care specialist is looking at. Doesn't look like a whole lot. We will talk more about this area over here called the fovea. That's the area where you have the highest visual acuity. The other thing we have here is, they call it the optic disc. It's also called the scotoma, S-C-O-T-O-M-A. It's the blind spot. And it's where as you can see, all the blood vessels are entering and leaving. And it's also the area where the optic nerve is leaving to go back to the central nervous system. And so because you've got, if you like, all the plumbing, the arteries, the veins coming and going, and the nerve leaving, you can't have yet all the layers of cells that are involved in vision on top of that as well. So that little area is the scotoma or optic disc or the blind spot. And you can all go out and things, but as you can. Well, I don't think so good anymore. I haven't chewed any bubble gum lately, but you have the old comic in there and have the cross and the dot. And move it, look at one and move it back and forth, and eureka. I think it's still in some psychology books. The other image disappears. That's because that part of the image is falling on the scotoma or optic disc or blind spot, and so you don't see it. Now you don't see a blind spot. You say, well, I'm looking out there, I don't see a black spot out there or a blind spot. That's because, well, first of all, if you've got both eyes functioning, one eye seeing slightly different than the other, so it fills in. Second, your eye is very seldom steady enough to see it. And thirdly, even if you only were using one eye, which can be done very easily by closing one of them, you don't see it because the brain tends to fill it in. The brain makes wonderful guesses and fills in what it thinks is there, or what should be there. So that's why you don't really see any kind of blind spot when you're looking out at the world. Okay? Well, according to that, and the computer, it says I'm supposed to let you go. Unless you have questions.